Welcome back, friends. So, welcome to the second class on quantum field theory and quantum entanglement. So, we had been looking in the previous class. What we did was we went through the course structure and the requirements, essentially various requirements. So, just to recap, we went through what are the required books which we will be following, and we went through so what are the basic requirements, what are the prerequisites, and so on. And then I also referred to you several books for your background information, and I also told you about the books which are required for this present day for this present course essentially. So, for this course I mentioned you these textbooks essentially which you can refer. And the course overview is essentially we start with the review of classical field theory and then introduce you canonical quantization with the scalars. This is precisely what we are trying to do in this course essentially. So, in the present the rest of the topics we will see as they keep coming on essentially. So, we started with the canonical quantization of a scalar field. So, today we will continue that in our class essentially. I just introduced you this Lagrangian, but it does not matter. So, we will start again. Okay. So, so the first topic we are going to do is canonical quantization. What does canonical quantization mean? So, if you remember canonical quantization, so this is a review from classical mechanics essentially. So, if you remember, and how do you go from classical mechanics to quantum mechanics? So, this is the same procedure which we will try to follow also in this particular case, but I will tell you the differences. So, in classical mechanics we define a Lagrangian to be a function of L Q dot T, where Q is a generalized variable. Which we will also call as canonical variable, the canonical variable of Q which we will define as now the generalized variable, and the canonical momenta of this variable is defined to be Pi. You can have n number of Q's. L is a function of Q dot and T, which is the Lagrangian, and Pi is L partial derivative of L with respect to Qi dot. Okay. And similarly you can have large number of Pi's also. The Pi's could be equal in number as many as Qi's, and with this we define a Hamiltonian sigma I Pi. Now, this is all quantum completely classical mechanics. Okay. We have not done anything field theory or quantum mechanics here. So, now this is what we know about classical mechanics. This is how we define Lagrangian and Hamiltonian two functions in classical mechanics. The Lagrangian is used for defining the action principle, the Hamiltonian is the energy, and which is defined also in quantum mechanics. Now, how do you move from classical mechanics to quantum mechanics? So, you take the conjugate variable Qi Pi and impose quantization conditions. So, you are taking canonical variables essentially which are the generalized variable and its canonical momenta, and impose the quantization conditions. This is how one moves from impose quantization conditions these are your canonical quantization conditions. This is how one moves from classical mechanics to quantum mechanics. Now this now we want to do the same thing for field theory, essentially that is the basic idea essentially. So we want to do the same thing for field theory. For a small point, just let me allow me to put H cross, okay, for a small period of time, okay. Then I will anyway set it back to this thing to 1 essentially. So basic idea is define a canonical conjugate momenta for the canonical momenta for the generalized variable and impose quantization conditions in terms of commutation commutation relations between the variable and its canonical momenta in terms of high H cross. This I think should remain in classical in quantum mechanics. This is nothing but your uncertainty principle. Okay, there is no delta because this is nothing but your. So you have this uncertainty principle which is x px is equal to H cross. This is how you define the Heisenberg version of quantum mechanics essentially. Now if you have a state, say psi of t and this all of you know that if I want to see the time evolution of this the state psi of t essentially. So this just becomes h, the operator h acting on psi of t. So the Hamiltonian is nothing but the time evolution operator, the Hamiltonian. So this is how you move from the Schrodinger picture to the Heisenberg picture, and in the no, you can solve this equation of course, but you can solve this equation. A formal solution for this is equal to e power minus I h t psi of 0. This, okay, we all know this is the time evolution of a state at a time t is equal to 0. How does it look at time t is given by e power I h t. In the Heisenberg picture, the operators okay, okay, in which states are dependent time independent. Okay, this in the Schrodinger picture the states move with time. Okay, in the Schrodinger picture the states evolve in time. In Heisenberg picture states are time independent. So they do not really evolve in time, there is rays in so they are rays in some vector space essentially. So you move from one state to another. In the Schrodinger picture it is like wave functions, so the wave functions evolve in time and everything. In the Heisenberg picture the states are time independent, but the operators, okay, the operators evolve in time. Absorb all the time evolution with them. In the sense that let me give an example essentially. So if you have an operator okay, so consider an operator O sandwich between two states which are at psi of t essentially, okay, sandwich between two states which are of psi of t. This you can write it in terms of psi of 0 state which is fixed, e power minus I h t O e power minus plus I h t psi of 0. Okay. Of course, there is a h cross which I have not put essentially here, there is a h cross. So, if the operators evolve in time, how do they evolve? You can observe this time evolution inside the operator in the Heisenberg picture in terms of I h t O e power plus I h t. So, the operator, if it is a states which are evolving in time, you only have one e power I h t coming for the state, and if it is an operator you have both the sides which are coming with the I e power I h t. Okay. Okay. So, this is something I think I made a mistake with the minus sign here. Okay. Okay. So, this should be correct essentially. So, this is correct. So, the operators evolve in time in the Heisenberg picture. Now, the canonical quantization happens in the Heisenberg picture, happens in the Heisenberg picture. So, the canonical quantization now, before moving further, okay, I would also like to review one more basic point essentially. Okay. So, you understand that what is canonical quantization? Canonical quantization is take any classical Lagrangian, you have a conjugate momenta, a conjugate generalized variable and a conjugate momenta, and impose these quantization conditions. These quantization conditions are nothing but these quantization are nothing but your commutation relations between the variable and its conjugate momenta qi pj in terms of IH cross. Now, this is exactly like the uncertainty principle condition. This is exactly like the uncertainty principle condition which appears in quantum mechanics. You have the same uncertainty principle. You can write x p x, you can write x bar, p bar, IH cross del, so on so essentially. Now, then I move to the difference between Schrodinger picture and the canonical and the Heisenberg picture. In the Schrodinger picture, the states evolve in time because the wave functions evolve in time, whereas in the Heisenberg picture the operators evolve in time, and we have given an simple example. Okay. This is all if you want a review of your basic quantum mechanics essentially, but it is also an introduction to your canonical quantization, what exactly canonical quantization means. I also need one more step, one more basic revision before going to classical field theory and doing the same process of canonical quantization to a classical field which we started yesterday. This is a review of simple harmonic oscillator. Okay. So, let us proceed further and review simple harmonic oscillator. The reason why I am doing this review of simple harmonic oscillator is because what we will see is when we do canonical quantization of the Lagrangian of a scalar field, essentially of a scalar field, relativistic scalar field, it will turn out to be looking very similar to the simple harmonic Lagrangian essentially. It is a simple harmonic oscillator Hamiltonian rather than the Lagrangian. and that is precisely the reason I wanted to review this simple harmonic oscillator in quantum mechanics, which is a very essential part which we need to do essentially. So, the Lagrangian of the simple, sometimes I keep calling it as SSO. So, I just introduce you this of the simple harmonic oscillator can be written as L is equal to half q dot square minus half omega square q square. So, normally we write m omega square q square, I choose m is equal to 1 for the present, okay. Just say for the present I set m is equal to 1, okay. Now P, the conjugate momenta P is equal to del L by del q dot, which is nothing but q dot. You can see it from here, there is only one term which is q dot square, and so P is equal to del L by del q dot, and the Hamiltonian is equal to P q dot minus L, and that will be just half P square plus half omega square q square. This is your Hamiltonian of the harmonic oscillator, okay. Now I want to define two creation and annihilation operators. These are this is something which we do standard in your quantum mechanics class. So, I just want to revise it essentially. So, we solve the harmonic oscillator solution in terms of creation and annihilation operators or the ladder operators, okay, A and A dagger. H cross omega p. Now these are A and A dagger are linear combinations of Q and P, but with the weights given in such a way that these A and A dagger operators, what kind of operators are they? These are Hermitian operators and so on. So, these are which we know actually, so that they keep that is the thing, the coefficient I missed a factor 2 here. So, the coefficient should be the same. So, plus I 2h cross omega p minus I by 2h cross omega p. So, omega root of this q, these coefficients are chosen in such a way that when I write the Hamiltonian, so that A dagger is equal to 1. So, the commutation of A and A dagger operators is equal to 1, okay. A and A dagger operators is equal to 1, and the Hamiltonian itself is just given by h cross omega A dagger A plus half. This is all something which you already seen in your quantum mechanics courses and so on, so, but I am just revising it. So, you define this creation and annihilation operators such that A and A dagger should, the commutation of A and A dagger should be equivalent to 1. Do you remember Q and P commutation is high h cross essentially, whereas A and A dagger is equal to 1. You take the coefficients in such a way, okay, assuming that mass is equal to 1 here, all the mass is 1, the coefficients in are such a way that the linear combinations of QP will set A and A dagger equal to 1, and the Hamiltonian looks exactly like this particular fashion. So, H cross omega is equal to A dagger A times plus half essentially. So, the commutation with the creation and inclination operator of the Hamiltonian is equal to A dagger H cross omega A dagger Hamiltonian acting on A commutation is equal to minus H cross omega A. The A operator is the annihilation operator. It is defined that it annihilates the vacuum, and whereas the A operator is the creation operator. It creates a state from the vacuum, it creates a state in the vacuum essentially. So, the ground state, if you take this ground state, the ground state should be annihilated essentially, it should have 0 energy. Okay, we will come to that part a little bit more essentially. So, the ground state is defined in such a way that the annihilation operator annihilates it. So, the annihilation, not the Hamiltonian, okay, the annihilation operator annihilates it. So, A is defined in such way that the ground state is equal to 0. That is the definition of the A operator. The A operator should annihilate the vacuum. Okay. So, now you can define an nth excited state. The nth excited state can be written as n is equal to 1 by root n factorial A dagger acting n times on the vacuum. So, the first state, you should remember the first state is essentially 1 factorial root essentially A dagger acting on the vacuum. So, it gives you the first state. So, the nth state is given by A dagger acting n times on the vacuum state essentially, A dagger acting on the nth state n times on the vacuum. This is crucial for our understanding of the canonical quantization of the scalar field. Now, this is all quantum mechanics, but what I wanted to represent that you have one for a given frequency, omega, you have a given frequency of a harmonic oscillator, you have an annihilation operator and a creation operator for a given frequency of a harmonic oscillator, and then it creates a state n number of states depending upon its energies. Essentially, it can create states from the vacuum state by applying the creation operator n number of times on the vacuum state. The annihilation operator, it keeps going down all the way such that the lowest ground state, which is the ground state, okay, ground state is annihilated and it gives to 0, that is A of the ground state is equal to 0, that is the equation I have written initially. That in fact becomes the definition of the thing. The energy of the nth state is given by En is equal to n plus half h cross omega. Of course, you all remember these formulas, I am sure you all remember these formulas. Okay. Okay. And so, this is what you get essentially, this is what you know the spectrum of the simple harmonic oscillator in terms of this A and A dagger operators, which is in the creation and annihilation operators. Of course, you can go into the Heisenberg picture and in which you can solve for the Q and P, how does the Q and P operator change essentially with respect to the time. So, for that this will be useful to us later on. Okay. So, the Q, I will repeat it again, essentially that is equal to e power I h t. First, okay, let me solve for Q in terms of A and A diagram. Solving for Q and P in terms of A diagram. What we get is equal to, we had reversed the equation. So, Q is equal to, if you sum A and A diagram, okay, is equal to h cross by 2 omega A plus A diagram, and P is equal to minus I root h cross by 2 A minus A diagram. This can be easily seen. You take these two equations, you take these two equations, add them, you get Q, and you subtract them, you get P, and so on. So, essentially, okay. So, you have this solution. With this, you can define Q of t in the Heisenberg picture, because in the Heisenberg picture the states do not evolve with time. So, you have evolution with respect to the operators. Time evolution is in e power I h t. Actually, there is a h cross, but anyway I have been neglecting it. So, minus I h t by h cross. Okay. This is equal to finally h cross by 2 omega A e power minus I omega t plus A diagram e power I omega t. You can have similar relation, okay, because the operator Q evolves, this is expressed in terms of A and A diagram in this particular fashion, and similar expression you can also give for P. Okay. So, the expression for P is given in this fashion. You can solve it for yourself. P of t okay. Now, again, just to revise ourselves, essentially that we have solved the simple harmonic oscillator, which again we use the quantization conditions. Okay, okay. We solve the simple harmonic oscillator with the Hamilton given by this I q dot square, which is nothing but x dot square, half x square, omega square k square, essentially m is equal to m omega square k square, root k, m by omega is k, essentially sometimes we write it as k x square, but I wrote it in terms of generalized coordinate instead of x, essentially that is the only difference. Instead of x, which we normally write, we wrote it down in terms of the generalized coordinates. This is half mb square, essentially instead of half mb square or x dot square. So, but instead of that, because we write it in terms of the canonical variable or the generalized variable, we wrote it in this way. And the conjugate momenta is P is equal to del by del q dot. With this we express our Hamiltonian in this particular fashion and define our creation and annihilation operators in such a way that A and dagger is equal to 1. So, we are imposing our quantization conditions on this, and this gives you the spectrum of the quantum harmonic oscillator, and such that the creation operator is an operator which acts on the vacuum, creates a state, a higher level state, one step higher, whereas with a frequency h cross omega, the energy of the state is increased by h cross omega. So, if it acts on n, it takes to n plus 1 state with an increase in the energy of h cross omega, whereas this can be seen clearly from the Hamilton commutation relations with the Hamiltonian, whereas the annihilation operator reduces this energy of the states with minus h cross omega, and that is how you can get the entire spectrum of the harmonic oscillators. and you see the harmonic oscillator, the spectrum for the nth state is essentially is given by n plus half h cross omega, where n is equal to 0, 1, 2, 3, the whole numbers essentially. Okay, I missed to write this thing essentially. And finally, I made a small remark saying that if you want to go back to the Heisenberg picture, okay, you want to really see that how the time evolution is in Heisenberg picture, you have to look at that time evolution of this state. Instead of seeing it in state, we have to see it in terms of the operators. For that, I have derived these formulas, because you have to write the Q's in terms of A and A dagger, and you see that both the A and A dagger operators also evolve in time, and accordingly Q's and P will change with time essentially. So, I will stop here and I will continue in the next class. Then we have now the prerequisites for quantization of a scalar field. Okay. We know what is canonical quantization, we know what is harmonic oscillator, and we will see how these two concepts get tied up in the canonical quantization of a scalar field. Okay. See you soon. Thank you. Welcome.